I'm recording the screen. Bill says proceed.
Okay. So, unlike Joe, I'm not going to do a lot of real-time coding because I don't type very cogently, and that would be really boring for all of you. So I went and stole all the code examples, not all of them, but most of them in here from Chris Allen's book. Please don't put this up publicly because I haven't asked him to actually share this. This is a private gist. I'll make that available to any of you that want to look at this stuff. And of course, it'll be on this presentation. So last week, Joe gave us a presentation on Functor. This sort of follows on from that. Functor is a really cool higher level function that allows us to, see things in a higher abstraction. Today we're going to talk about applicatives, and applicative has the applicative class, which describes the two functions that we have to have to make things applicative. So in other words, if you create an instance of applicative, you are required to fill in the magic for pure, which we haven't seen yet. We'll see that again in Monad when they talk about return, which is kind of the same thing. It just takes a value and it puts it in an applicative context. And then this other thing, which doesn't seem to have a really good name, some people call it AP for apply, or a TIE fighter, which I'll use in this thing, and then some other folks call it Anglars. I don't know why. Anyway, so you remember last week we talked about FMAP, and FMAP, we have another stand-in sort of symbol for this, and it looks like this. We take a normal function that takes something from A to B, takes an A as an input, outputs a B, and it basically, if you give it an A that's associated with this structure, it'll spit back a B. In other words, it does a transformation inside of that structure, but it returns a functor again, and that thing will be transformed from A to B. So this applicative is very similar to that with this TIE fighter here, in that the function is now, it has some structure associated with it. So if you sort of squint and ignore that, the F, which is the functorial brilliance there, it looks almost exactly like the FMAP, except that we see now the function. We have to take care of the fact that the function, for instance, in a maybe context, the function may itself not be there, right? So everybody sort of follows that. And of course, we saw from last week that that there is a sort of a shorter name for these things called lift, right? There is an applicative form of lift. That's not what we're looking at right now. We're looking at the FMAP analog for lift. All applicatives are functors, and so we kind of get that for free, although we don't get the lift for free. You have to put in the right package to get that, but the lift A is the same as FMAP, which is why it looks the same. You can sort of ignore line 20. I didn't end up using that. So some examples of how we would use, pure, and a little later the TIE fighter, and I included in here just so that you would be familiar with FMAP. If you elevate this function, if you pull this function up into this applicative space, then the proper way to do that is to use this TIE fighter, And so again, we have a function that's in this context that has some structure. So now they're sort of on the same playing field, and we can do the same thing that we did with fmap. We just take the function, we pull it up into that space, and then we can run it over the the list of 1 to 3, and we get 2, 3, 4. It does the same thing fmap does, but you can think of it like that. A few more examples. If I take 1 and I sort of cast it, I tell it what kind of structure that I want it to be in, I get a 1 in the list. If I say it's a maybe int, I get just 1. Anything confusing about any of that? Pretty straightforward, right? And I'm going to answer your question at the end.
Okay.
As Joe pointed out, you can only map over a structure that has this kind of kind. So it's something that's waiting for a value. So if I'm showing here that if you take the kind of either string, you get something that's waiting for something, right? So it's either, for our purposes, the structure here sort of grabs that thing that's right on the left. It's on the left side. So when you fmap, you're fmapping over either string or either int or whatever it is, and it doesn't kind of get touched by that fmap operation. Same thing with maybe, right? Star dot star, or star arrow star. This one's a little more complicated. This function, the tupling function. So what do you think this does? I'm pulling 1 up into and sort of giving it a hint here, right? I get the right 1. Being because the left side A is not getting considered, but it's putting out the int. There's another example. I pull 1 into this the context of maybe, and it ignores the left side, so that when I say fmap plus 1 over this tupled thing, voila, it ignores the left side but bumps the right side of this. So just to keep all of us honest, we have these 3 forms. They look very similar, just normal function application, an fmap, and then this new thing that we're talking about is the function being associated with some context that we have to deal with in a special way. So the take home for this is that our function is embedded in the structure. We still need to apply the function over the structure that's the target of that, but now that our function also has some structure as well. So we have 2 bits of structure that we got that we kind of have to glue together. And we'll find out that that's why they sometimes call applicatives monoidal, because there's a part of it that where you. Why is that funny?
Monoidal.
Okay. Because you have to glue together 2 kinds of structures. One of it's coming from the F-ness of it, the functorial part of it, or the structural part of it, and then there's a separate thing that causes the mapping on the right side. So let's look at a couple examples of just sort of using this. In this case, the structure that we're talking about is listness. If I have a list of 0 or more functions, and I do this special kind of mapping, I'll get sort of what's the term for that? Cartesian coordinate, a Cartesian product of those things. So I'll get a ×2 on a 4 and ×2 on a 5, and then I'll get a ×3 on a 4 and a 3 on a 5, and that all turns out. You can see that it's made a choice about how it's doing the addition, right. the concatenation of the terms, right? It's opinionated about that. So another example, if I elevate this guy up and put him in the maybe context, so I'm doing ×2 ×2, I get just 4, it works predictably for the nothing case on either side. If I do a just times 2 and a nothing, I get nothing. Or if I do a nothing and a just 2, I get a nothing.
Can you do nothing times nothing?
Yeah, and you'll get nothing.
But how does it know that nothing has a multiply?
That I don't know. I probably would say that you haven't given me enough. It's bottom for both cases, so it probably would just say nothing, and it would be happy with that. We can try that in a minute. Remind me, we'll give that a try. So nothing. In fact, let's try that right now. But I warn you, my typing is. So I'm going to say here nothing, and I'm going to say TIE Fighter. Nothing. And it happily did it. So let's see. I said that applicatives are monoidal. I caution you about taking that too far. That can get you in trouble because you have to pay very much attention to which monoid you're using and how it. Sometimes it does things that are a little bit of a surprise. Let's take a look at this case here, right? If I fmap +1 over this tuple, it ignores the left side of the tuple, and it fmaps the 1, right? Same thing. This is we'll take a look at the applicative for 2-tuple in a second when we do the TIE Fighter. But if you do an info, and I won't do that in here, take my word for it. If you do an info on tuple, you'll find that one of the many that spits out, in other words, all the instances of the tuple case, you get the definition for the data type here, and then a little while longer you'll see that the applicative for tuple, given some value on the right side, that value has to be monoidal. I have a mistake here.
What's your mistake?
The monoidal thing should be on the left side. Anyway, we'll see in a second how that actually works, and I'll clean this up with something that's not quite
Isn't
right.
it? I mean, you've got your.
Do I have this right?
Yeah.
Anyway, you notice that there's no it's referring to line 102. You notice that there's no need for a monoid for B, because B is the thing that gets mapped over. Thank you. A couple of simple exercises now using the applicative. The monoidal applicative, if I have 2 tuples here, it concatenates the 2 on the left side and maps the 1 on 0. Right?
Where did the string concatenation behavior come from?
It comes from this magic right here.
This is the applicative of writer.
Oh.
So that's something that's not particularly. I thought it was interesting that that's the behavior of this particular thing, because applicatives are monoidal. You get this. I don't know. I didn't search carefully enough into that to find out. Here's another example of this. If I have a tuple on the left side, I have a sum of 2, and on the left side a sum of 0 here, concatenates those in the right way. In other words, it adds the 2 of them together. So that's why you have to be careful about this monoidal bit. It did the right thing on the left side. It summed 2 and 0, right? Because that's the particular monoid for num, but the sum version of that. So it did the right thing there, and then on the right side it mapped 1 over 0.
Isn't that also the correct type? I'm confused as to what you mean by you have to be careful.
Well, stay tuned.
Oh.
So if there's more. You get the steak knives. So if obviously if you were only looking at this, you would think that that's what it does. It adds the two things together. But if you choose this version of num, the product version, it also does the right thing, right? So 3 times 2 is 6, and then mapping 9 over plus 9 over 8, you get that. Does that answer your question?
No, makes
Just be
perfect
careful
sense.
about what monoid instrument you're using and understanding how it actually works. And it doesn't do a point by point. It's doing a Cartesian monoid, right? It's not like if you looked at zip width. Zip width is just another example of this under the covers, right? But it does a different. It has a different MAPN. Are we getting questions?
Yeah, I'm a pen, that's what it was.
Okay. So with the list applicatives, we're mapping lists of functions over list of values, right? We already talked about this and why that works. What we're really doing is this on line 141, right? We're doing a yes, we're doing an F map for the first thing, and I sort of think of it like this: that on line 145, you're F mapping this thing that has 2 holes in it over the very first target, and it's sort of like saying, I don't know how accurate this is, but I like to think of it this way. I'm creating a list of functions to begin with this first mapping, so now I end up with a list of +1 and a list of ×2. That should be +2.
Yeah. We get the point.
We get the point.
Yeah.
Anyway, so the first one is an F map. These should both be this should both be pluses and no times in here.
It's left associated.
And then pardon me?
Is it left associated with neither?
Well, it does the first thing first, right?
Okay.
Because you're partially applying this, right? You could think of it like that.
So like 1 plus or +1.
Does I don't think it makes any difference.
Yeah.
But because this whole thing is probably not Haskell-y accurate, but that's the way I'm thinking about it. And then when you do the second part of the operation, the non-mapping part, now you have structure around those functions, and then now we have to do this, right?
Why is it ×2 instead of plus?
Because I made a mistake.
Oh.
It should be plus, obviously.
Yeah.
Right. So another example using the 2-tuple case. It's basically the same thing. You're filling 2 sides of this function. The first one is an F map because
So you get 1.
there's no structure, there's no function yet no function in the list, and then you pick that up, and then you have to use the specialized case.
We have 1
comma
empty,
space,
1 empty.
Yes,
Then
you should have 1 empty, 1 empty,
and
2
then
empty. 1 empty, 1 empty, and then when you tie it together, you'll pick up.
Wait, you
Because
get
then you'll end up
empty,
yeah,
1
that's
empty,
correct.
2 empty,
Yeah.
and then you'll end up with 1 empty, 3, 1 empty,
Yeah.
4.
Yes.
I should have put that in. Oh, I did, right down here.
Yes.
Yeah.
Then apply 3 to 4, you get 1 empty. So you start off with 1 empty, 2 empty, and now we have structure, and I'm applying it to 3, 4, and you end up with that whole thing. There's also a lift version of this.
Good examples.
Hmm?
Good examples. Like
I stole them from
good stuff.
Chris Allen, yeah. I thought they were good.
That's good.
Why is all this useful? So this
Yeah,
goes back to your question. I want to point out that we actually saw this, even though maybe a bunch of you didn't actually go to the homework, and because he told you to go and look at asin.data or data.asin. You'll notice that right up here, there's a little descriptive verbiage about. In fact, they even use person. And you will see if you look very carefully, he's describing here how you would go about if we were going to use person as a data function, and we were going to map person over some JSON values, esin values. How would we go about filling, creating a full object here, if you want to call it an object, right? Yeah, you notice we're using tiebreaker here, and also the first one is an F map, right? And then we have these 2 other functions. I would ignore this. This is just pulling this out of this object, and this is a combinator for getting this stuff out of that object, and then using that whole value and applying it to the same thing for age, right? So we already actually saw this last week or 2 weeks ago, and you might have been curious about it. I got sort of sucked into this because I knew I was doing this thing, and I probably spent more time on this than the past. I think we're going to do it again this week coming up. I also found an example of Brian McKenna. Some of you may know him. He's a big wig in both JavaScript, Scala, and also programming languages. Really incredible guy. I found this on his site. Here's how they do it in Scala, right? So this person has a name and an age and a postal code. This bit of ceremony here, I suppose, curries the person to start, and we go from right to left because they're wrapping each of these as they go out. So the first thing is the name that gets done, then the age, and then the postcode. And you can see that the very first thing is a map, right? So they're, I don't know if they have an F map. I think everything is map.
In Scala.
Even when you're doing a list, not doing lists, I don't know. I don't know what they do with maybe because do you do?
I forget.
Okay.
You talked about the optional class in
I'm
Scala?
talking about if I were to do fmap on the curried person, would I use the term map, or would I if the thing that I was the target that I was trying to get to is a maybe person at the end, would I use map, or would it be something else?
Well, I'm having a little bit of difficult time understanding this example because, as you pointed out, like applicative functors and functors, like there would be a piece of indirection in between the name and the person, which would be optional, right? Or Scala's version of maybe. So I would expect to first take this person constructor and put it into the functor context, which would be optional in Scala's case, using the $one or whatever.
I think the answer is, and I want to talk about this in a second. I think the answer is that it kind of picks it up from the other values that are in those, because if you think of a name would be something that you'd either verify, or it would be something that didn't exist.
Oh.
Right, and that's how you end up with the maybe.
Okay, so well, if name map person create, yeah, I don't understand the Scala.
Well, let's take a look at how.
But I do understand the Haskell version.
Let's take a look at the Haskell. So let's say we want to create a smart constructor for person, and what we know is that we could either create some functions that would use maybe a kind of a validate function to create a maybe string, right? Because we don't know whether that's going to be successful, and the same thing for address, right? So what's kind of hidden here is that we're gonna create a smart constructor for person, and we may be either missing or invalid name and address, right? So we want something like this: make a person that takes a couple of strings, or a name and an address if we want to new type those. And at the very end, we'll end up with a maybe person, where any of these things could kind of fail, either for validation reasons or because they just didn't exist. So I show a little thing here of how you do make name. It takes a string and produces a maybe name. Same thing for address. Make address would take and it would do it like this. It would fmap name over this some kind of function, right? You could think of it as just, you would end up with a maybe anyway if it just didn't exist, right? So this is kind of out of the book, and he's kind of complicating this, right?
I got you. So like say validate length 25s. If s is like of length 20,
here you
you
go,
get back
right
nothing.
Here. You get nothing, and then this thing would fail, at least on the name size, the name size, and it would constitute at the end of a failure. You would end up with nothing instead of a just person.
Mm-hmm. Yeah.
It would be an unjust person, right? So and so now we know that that the very first F mapping, when we choose the make name version using person, we end up with a maybe, and we end up with the thing that it's waiting for. The next thing it needs is an address, right, which would complete that. But we're ending up with a function from address to person, because that's the next thing after we partially apply it. And voila, it's stuck inside of this structure here, right? So we can't f-map the next thing, because it wouldn't work, right? So what we would be trying to do is something like this. So let's say I had a maybe address, which was the next thing. I'd be f-mapping. This is the first one, the f-map person, using the make name, and then I'd want to f-map that whole thing using the f-map person make name on this maybe address, right? So because the f-map won't work, we need something more powerful, because now the thing that comes out of this thing in the middle here is a maybe name, right? So we're stuck, and you would get this exception here. It would spit out. It would say, I can't match the expected type addressed to some type B with the actual type of the address to some type B, but it's stuck in this structure. So what we really need is something like fmap, the first case here, and then tie-dye it into maybe address, or the much nicer form, which we're familiar with now, because we're going to take this person, bang it over make name, and then tie-dye it into address. And that's essentially what we saw here, going back to the Eason example again. This is how they do it when they get the from JSON. So they're creating a from JSON. They're creating an instance of from JSON for this particular person object. And you see this all over the place. Alex and I were working on some code, and by the time I caught up with Alex, he already had I couldn't find it this morning, the up parse thing. So you see it all over the place. It's a real common idiom in Haskell to sort of make objects in a clever way that have some potential structure around the functions that are included in that. So real useful. You'll see it in our code all over the place. So any questions? I hope I demystified applicatives a little for you. Any questions, Bill? Okay, so we already went over the homework last weekend. I haven't done the homework this week, so I don't know whether anybody wants to see the homework for the upcoming one. We can do it next week when we do. Who's doing next week's talk?
Next week we don't have a talk.
We don't have a talk.
We do have homework, but we don't have a talk. So
Okay.
we could spend next week as sort of office hours in case anyone gets stuck on applicative functors. I think that first week of applicative functors is probably easier than this last homework assignment with JSON. I believe that the next homework assignment is much more clear. But in the event that folks get stuck, bring your homework next week, and we'll just hang out, eat 3 sandwiches, and hack on the homework.
Cool. I'm all for that.
Yeah.
We good? Did that answer your question?
Yeah.
Good. So it is useful. Anytime you have something.
I wanted to ask, if they guys are using the functors and applicative functors in their real code, or is this just for learning?
Academic stuff.
Yeah.
Just for show off or something.
There are
Or-
some
or
parser
you-
libraries that do this, like parsec and the other things of
Async too.
parsec and the name.
Async.
Right.
Yeah, I guess you could think of this as
It says async 'cause it rhymes
being a
with JSON.
parser in a
Well,
way.
I mean, a thing that Hal showed that is important, I think, to realize is that the behavior of app and the behavior of fmap differs depending on the instance of functor, the instance of applicative, right? So maybe the maybe instance of applicative functor does a sort of different type of thing than the list instance. But there are also other instances of applicative functor, like the IO monad or something like that, which is your way that you interact with the outside world. So at a high level, they're all doing similar things. Like the type of applicative is this same. The types that appear in the applicative type class are the same, regardless of what the instantiating type is. But the behavior differs depending on which type is instantiating it. So we use, I know in the code base today, I'm fairly certain that we use the maybe instance of applicative functor. We definitely use the IO instance of applicative functor to take a pure function, like let's say something like person, and run a bunch of IO operations, get the results, and then pass those pure values to the person constructor. So we do use it quite a bit.
I think the JSON parsers also.
JSON parsers also, yeah, for sure.
Yeah, you can think of this as a parser, right? It's you're running this over JSON data, and it's not really returning another parser, but it's consuming that data and putting it into some form that is useful for Haskell. We also use quite a few ethers and or validators, and you could see, given what we were talking about, the particular monoid instance that you use here, you could see that it would be really nice if make name failed and make address failed, that you didn't just report back the first failure, but that you actually collected both failures, right? So the difference between the either and the validators, that validators usually have a little more structure around how you monoidally add the two left sides of those things, and you can just swap it in. You can just take out either and put in validator, and it voila, it just works because it knows how to do monoids the right way. So that's the beauty of this language.
Very cool, man. Thanks for presenting.
Thank you. It's fun.
Don't close your thing yet. I gotta stop the recording.
Okay.
Alexis is going to talk about monads, not this week, but the upcoming, not